Welcome everyone around the world to this new webinar of the International Solar Alliance. This is Dr. David Jacobs speaking here from Germany. We are having today session 27, which deals with market and system integration of solar PV. As you probably already know, this webinar session is supported, organized by the International Solar Alliance and the Clean Energy Solution Center. So thank you very much for providing this very important platform for solar PV experts around the world. My name is David Jacobs. I'm founder and director of the consulting firm IET International Energy Transition. Been working in the renewable energy policy sector for the last 14, 15 years now, publishing a lot of documents, publications around this, and working in more than 40 countries. So I've dealt with system and market integration issues of solar PV and other renewable energy technologies quite extensively, and therefore I'm really happy to share some of the lessons learned and some of the experiences. As you probably already know as well, this is part of a larger webinar series. This training course contains a total of 8 modules covering policies for distributed solar PV, large-scale solar PV, the future of policy, system integration, socioeconomic aspects such as job creation, the off-grid sector, the heating and cooling sector. And actually this webinar is part of module 5, which deals with system and market integration. So please be aware that this is only an introductory webinar. There is 4 more webinars on this topic of system and market integration. So please also check out webinar 28, which deals with the merit order effect, so the integrational effect of solar PV in competitive wholesale electricity markets. Also 29 is very interesting for you probably, which deals with a duck curve in the California electricity market and potential ways of how to mitigate the impacts of solar PV integration. And then also session 30 dealing with solar PV and the role of storage, and session 31 sector coupling using solar power in the heating and cooling and also the transport sector will be very interesting for you if you're interested in solar PV market and system integration. So here just a quick overview of what we're going to discuss in the next 45 minutes. First of all, we're going to have a closer look at the learning objectives, then try to understand the impact of solar PV on power systems, and also understand how we can design power systems, how to make them more flexible in order to integrate increasing shares of solar power. And as always, you'll get quite an extensive further reading list. And at the very end, also some knowledge checks, some simple multiple choice questions where you can actually check out whether you have understood the key takeaways of this webinar. So let's look at the learning objective. So we want to understand, first of all, the benefits of solar PV for electricity systems, because they're sometimes overlooked in our discussions. We also want to understand the very specific features of solar PV, also compared with other power generation technologies. To what extent are they different? To what extent do they impact the electricity system? And then secondly, we want to get an understanding of the different options that are available for making electricity systems more flexible and therefore to integrate solar PV more easily. So first of all, let's look at the features of solar PV and the impact that this has on electricity systems. First of all, the benefits, because in our discussions on solar PV integration, we always focus on the problems, which is fair enough because you need to solve the problems, otherwise you can't make it happen at all. But by focusing on the problems and the challenges, we sometimes overlook the very simple benefits of integrating solar PV in electricity systems. One of the major benefits, especially for countries which are importers of fossil fuels, is that you have fuel cost savings. And if you're a country which is like Morocco, dependent on 80–90% of fossil fuel imports, then installing solar PV is very beneficial for you and will probably also help to balance your overall economics of the overall economy. Then again, we see that solar PV has very short-term marginal costs. It has no fuel cost. The sun comes in for free. And this has a very positive effect, at least for the consumers in the wholesale electricity market, because it reduces prices. This is what we usually term the merit order effect. And as already mentioned before, in session 28, you will learn each and every detail about the merit order effect. Also, the next point, displacement of the most expensive generation units. By adding solar PV to wholesale electricity markets, you're actually shifting the entire merit order to the right, thus pushing out the more expensive technologies of the market and therefore leading to cost reductions for all of the consumers, or at least leading to cost reductions in the wholesale electricity market. And then last but not least, of course, the reduced emissions are also a very important feature of solar PV. And here I'm not only talking about reduced carbon emissions, which we tend to focus on mostly, but I also want to mention the emissions from stacks of coal-fired power plants or gas-fired power plants like NOx, SO2, which have very severe impacts on the health of human beings living in these areas, or even living in very far away from these areas, because the dispersion of these pollutants can be very far. And therefore, by reducing these emissions, by moving to renewable energy-based systems, we're actually taking away a lot of the health costs, which are implicitly integrated in our current electricity systems, and therefore we are reducing the cost for the economy as a whole by reducing the health costs, the negative health costs. But now let's look at some of the challenges. So what are the challenging features of solar PV? We have low short-run costs. That means low marginal cost. Sun comes in for free, which is very different to a gas-fired power plant or coal-fired power plants. We have variability in supply and uncertainty of when we're going to produce solar PV. And we also have locational variations in solar PV radiation. You might have some regions in your country where you have a lot of sunshine and others where it's more cloudy. If we want to structure this a little bit further, we can say, well, these low short-run marginal costs are actually very much related to the market operation, the wholesale electricity market, and that of course also to the finance mechanism or the support mechanism. Is solar PV able to finance itself on wholesale electricity markets, or do you need additional support? During what periods might it be cost competitive on wholesale electricity market? Might this maybe change with increasing shares of solar PV? You already learned quite a lot about this in the preliminary webinars on solar PV policies, such as feed-in tariffs, net fits, and so on. So please also check out these courses. Then we're talking about the uncertainty and variability, which is largely tackled by market and system design. This is going to be one of the discussions we will have in a couple of minutes from now. And then regarding the locational variations, we're primarily talking about grid expansion planning in the jurisdictions that you're in order to take, or in order to be able to benefit of the solar radiation that is available in your country and to bring it to the load centers in your country. So once again, the low short-run costs, the low marginal cost of solar PV, zero marginal cost because the sun comes in for free, is very important to keep in mind because, well, first of all, it has an effect on the merit order and wholesale electricity market, and you will learn more about this in session 28 on the merit order effect. But it also has an important implication for how to actually refinance solar PV in wholesale electricity markets. And in order to understand this, you really need to be aware that the cost structure of a solar PV system is very much different to those of, for instance, a gas turbine or a combined cycle gas turbine. And this is what I depicted here on the right-hand side by looking at the fixed versus the variable cost of different power generation technologies. So when you look at the very right side of this graphic, you see the fixed and the variable cost of solar PV. And it becomes very clear that 95% of the solar PV systems are actually fixed costs, which are related to buying the solar panel, the inverter, all the other equipment, to installing the solar PV plant. And then the remaining 5%, which is only related to some of the operational maintenance activities, such as cleaning the solar PV modules or replacing the inverter after a couple of years' time. This is really just a small fraction of the overall cost. And what does it mean for a solar PV investor? It actually means that once you buy the equipment at the very start of the project, you need to be more or less sure that you can earn the revenues, or that you earn enough money over the next 20 years, 25 years of the lifetime of the solar PV system in order to recoup these costs that you have paid upfront. The situation is very much different, for instance, for a combined cycle gas turbine, where you only have about 25% of your cost, upfront cost, capital expenditures, and the remaining costs, the remaining 75% of your costs are actually operational cost and maintenance costs. So buying the gas, maybe even paying something for the carbon emissions, operating the gas-fired power plants, and so on. So as an investor in a gas-fired power plant, I'm not so much concerned about how much money I will earn over the next 20 years, because I still have the option to just shut down my operation, because my upfront investment in the equipment is very much lower. So the risk for me to lose money is also lower. So therefore, we also see very different expectations when it comes to market design and when it comes to the payment duration of power purchase agreements. Gas-fired turbine power producers are happy with short-term markets, as we can see them in liberalized electricity markets, such as functioning in wholesale electricity markets, whereas in many cases, solar PV and also wind energy producers, which have these high upfront costs, are normally interested in more long-term contracts, even though they might have very low prices, as we have seen, for instance, from a lot of solar PV auctions in the last couple of years. The price might be very low, might be substantially lower than the cost of fossil fuels. However, solar PV and wind energy prices that we've seen in the recent auctions are normally part of 15, 20, 25 years power purchase agreements, so that the power producer actually does know that for the next 15, 20, 25 years, he can sell each and every unit of electricity that is produced with a solar PV plant at a certain price. So this is just a short introduction into that. As mentioned earlier, you can check out sessions 3 to 9 on support mechanisms, and also check out session 28 on the merit order effect in order to learn even more about this. What I'm now more interested in this webinar is variability and uncertainty issues which are related to solar PV. And this is very important to understand when we also want to understand how future electricity markets need to be designed. In order to get a good understanding of this, here just a few graphs on how future electricity markets could look like. This is an example taken from Germany, but you could also take other countries such as, well, you could take any market with very high shares of solar PV and wind energy in the systems, because the effects that these technologies have on markets and market operations are the same all around the world. This is just an example from Germany because we are already at relatively high shares of variable renewable energy technologies such as wind and solar PV, but it would exactly the same in India, South Africa, or California. So here is a week in early February where you have little solar PV in the system, quite a lot of wind because it's quite stormy outside. So you see that you have you see first of all solar PV coming in every day at a certain time with relatively sharp peaks. And then you also see that during some days of the week, especially the weekends where you have less demand of electricity due to industrial and commercial customers, you can actually see that the power supply of solar PV and wind energy and the other technologies is already exceeding demand, which is outlined here in the red line. So what you then would need in these days is already more flexible supply or more flexible demand. So we were assuming here that electricity demand is actually fixed and that it does not react to any of the supply activities in the electricity market. However, if you're able to increase demand flexibility, you could imagine a situation where then on a Saturday and Sunday, electricity demand also in the industrial sector goes up because electricity prices will be very cheap during those hours, and you might have an incentive to run your industrial facility during these times. Or what you could also assume, very low at the very bottom of this graphic, you see, for instance, biomass and biogas operating relatively stably. Only a fraction of the biogas systems have thus far been designed more flexibly with a storage unit next to it. And of course, you could imagine that flexibility on this level also increases, which would also allow you to integrate solar PV and wind energy more easily. So this is the week of early February. Now let's look at how it looks like in the summer months. Here's a typical week in 2022 in August. And now you can really see the effects of solar PV on the systems, meaning that you have very sharp ramps during the operation hours of solar PV. So when it starts operating at 8, 9, 10 o'clock in the morning, you see this very sharp increase of solar PV, which of course also means that other operators of power plants need to be able to provide the residual load, which means the load that is necessary to meet the demand next to solar PV and wind energy. And this is in this case indicated by the gray area, which is supposed to indicate the contribution of fossil fuels to the power system. So you can see here that the fossil fuel-based power plants that we need in such a system need to be able to ramp up and down quite significantly, and that they should also not have any base load or any must-run capacity, because they need to be able to fully switch down as well. And of course, this is not the case for all of the fossil fuel-based power generation units that we currently have in the system. And then also we come into situations like this. This is a week in late November 2022, where you can see that there's very little wind, also very little sunshine, because it's mostly gray in Germany during those months. And therefore, a large part of the electricity demand actually need to be covered by fossil fuels or alternative fuels. And therefore, it is also very important to have this backup capacity available in the system. So what do we need in order to make this happen? First of all, we need to improve weather forecasting. This has been a very big issue in many countries around the world. Here in the lower part of the slide, you can see a graph which illustrates in a very simple way the solar PV output on a sunny day, which is the top line, which is a very straight line and predictable line. And then you also see of an individual power plant the output of solar PV on a cloudy day. And then you see this very spiky movements in the output, meaning that it is very hard to predict the solar PV output of a single solar PV plant on a cloudy day. Of course, these variations get balanced out when you stop looking at a single solar PV unit, but instead of looking at all of the solar PV systems within your country or within your balancing area. And this already helps to smooth out some of the balancing, some of the fluctuations in solar PV. But what is definitely needed is also changes to the electricity market design. And this has been one of the most crucial elements of design changes to the electricity markets in many countries around the world, which are trying to integrate increasing shares of solar PV. And that is moving the gate closure times of wholesale markets much closer to the actual time of operation. Because previously in power systems, where you only had fossil fuels in the systems, you were normally operating with day-ahead markets, meaning that, for instance, today at 2 o'clock in the afternoon, I already need to tell the market operator how much electricity I will produce tomorrow from 5 o'clock in the afternoon to 6 o'clock in the afternoon. And then each and every power producer would do that. And then, of course, by running a gas turbine or a coal-fired power plant, I can actually really do this in the next day, even though it is 36 hours away from now when I make these predictions. This is, of course, much more difficult to do for a solar PV and a wind energy producer, because predicting the weather 36 hours from now is much more difficult than predicting the weather 15 minutes from now. And therefore, by moving the gate closure time is much closer to the actual operation time, and by introducing additional intraday markets, which operate maybe 30 minutes from now or 15 minutes from now, we have actually been able to much better integrate solar PV into the system. What is sometimes overlooked as well is the capability of solar PV, or particularly solar PV inverters, to help to stabilize the electricity grids. Because from a lot of policymakers around the world, I still hear, yeah, but solar PV is actually destabilizing the system. We cannot integrate more. But when you really look at the state-of-the-art inverters that you have, they can actually help to provide very important services to the electricity grid, mostly to the distribution grid. They can supply reactive power, they can support voltage dips and provide voltage right-through capabilities. And this, of course, is very important for stabilizing distribution grids with increasing shares of solar PV and wind energy in the system. So actually, the story is now different. We can actually say by implementing solar PV and wind energy to our distribution and transmission networks, they can actually help to provide some of these very services. And in order to allow them to provide some of these services, we also need to adapt our ancillary services market, because in the old systems, they frequently have not been able to participate. So for instance, we need to minimize the bid size, because solar PV and wind energy producers might not be able to bid the same amounts of capacity that fossil fuel-based power generation has. We also need to maybe reduce the time periods. We say we're looking at 5 minutes intervals, 10 minutes intervals to provide these services, and so on and so on. So there has been a lot of lessons learned about how to also adapt and change the ancillary services market design to allow solar PV to participate in those markets. Now, just a few words on the last feature of solar PV, which is very different to those of fossil fuel-based power plants, and those are the locational variations. Here's a map of Spain where you can see the radiation of solar PV changing quite rapidly from the southern part in Andalusia to the northern part of the country. And of course, you want to be able to benefit from solar PV where it is where the sun is mostly shining, and therefore you also need to adapt your transmission grid expansion in order to capture these benefits. And here's, for instance, the electricity system planning of the European Union, where you can see that major bottlenecks, for instance, between Spain and France, here indicated with a red line, have been identified. And then in order to come to more electricity trade, also to allow for solar PV generation from southern Spain to be transported all the way to France or even further to Germany, these grid bottlenecks need to be overcome. And what is also very important to understand is that once you establish renewable energy targets, for instance, you say we want to have 40% of renewable electricity by 2030, then of course you need to also adapt your transmission grid expansion planning and come to a situation where this is actually reflected in your transmission grid expansion planning. Here just another example, this time not from Europe, but from Africa. This is IRENA's Africa Clean Energy Corridor, where they actually started to look at the existing transmission lines within Africa and also overlaying it with the solar radiation that you have in different parts of the continent. So they were then trying to create this clean energy corridor from the northern tip to the southern tip of the continent, and also trying to cooperate with the regional market operator, with the Eastern African Power Pool and the Southern African Power Pool, to see what kind of measures are needed in the market design in order to integrate solar PV and other renewable energy technologies more effectively. And what is also quite interesting about these initiatives is that in these predefined areas, which are part of the clean energy corridor, also project planning for solar PV is becoming less tedious. For instance, you are requested to have lower environmental impact assessment requirements than you would have it in other parts of the country or in other parts of the continent. And therefore, hopefully, this initiative will lead to a situation where you see more solar PV being integrated in these different power pools in these different countries, and doing this in a way that it is very much aligned with power system planning. So now let's look at some of the options that we have for making the power systems more flexible. And I've listed here 6 major options to make the power systems more flexible in order to integrate increasing shares of solar PV. We've already looked at one of them, and that is flexibility through grid expansion and interconnections. That, of course, by increasing my interconnections with my neighboring countries, I can import and export solar PV more easily, thus reducing also the impact that solar PV has on my wholesale electricity market. This will be further discussed as well in session 28 on the merit order effect. Then secondly, we're looking at the flexibility from conventional power plants, then the flexibility of dispatchable renewable energy technologies such as hydropower and biomass and biogas. Curtailment rules for renewable energies are also very important. And then definitely also the flexibility of demand and flexibility through additions of storage. Just to highlight one thing here, sometimes people ask me what are actually the most cost-effective integration options for my country. And here, this really depends on the options that you have available. So if you have the opportunity to interconnect more with your neighboring countries, to just expand your transmission grid and to have more market integration on a regional level, this is usually considered a very straightforward and also cost-effective PV system integration and market flexibilization mechanism. What is also normally considered as a very low-hanging fruit is more flexibility from conventional power plants. Sometimes it just takes changes in the operation of the power plant. Sometimes it just takes a few design changes to the actual physical structure of the power plants. Flexibility of dispatchable renewable energy power plants is also quite a low-hanging fruit. And then normally the demand side flexibility and flexibility through storage are considered more costly to a certain extent because they are not such low-hanging fruits. However, when you say, well, I live in a country or I live on an island and I don't have the chance to really expand my grid to my neighbors, I don't have any dispatchable renewables, and also my conventional power plants cannot be upgraded very easily, then you actually might get to a situation where curtailment of renewable energies and also adding storage to your systems might become a very important option for you quite soon, even with relatively low shares of solar PV and other renewables in the system. So this is just to say that you really need to come up with a specific national analysis or regional analysis to really see which of these flexibility options is most cost effective for you and in which order you should pursue them. Here's just some indication given by a research team from the National Renewable Energy Laboratory in the US, where they have kind of structured them, first of all, along the different lines of intervention, system operations, services from variable renewables, demand side intervention, load interventions, more flexible power generation from fossil fuel-based power plants, transmission expansion, storage. So as we've discussed them before, but then also indicating as far as this is possible, to what extent these are more costly or less costly options. So for instance, when you look at the very left corner, you see that improving renewable energy forecasting is actually one of the lowest hanging fruits, and you should definitely do this to improve market integration of solar PV. Whereas on the very right-hand side, when you look at the storage options and you look at chemical storage options, pump hydro storage options, these are normally considered the more costly options. But as mentioned before, you might be in a very particular situation within your country where actually pump hydro is one of your low-hanging fruits and one of the only system integrations options that you have available, and therefore you should already start tackling them straight away. So maybe you can just go through these different options after this webinar and also consider which ones of those you have already implemented and which ones of those might actually be helpful for you in the next round of making the electricity system more flexible. I also wanted to highlight that there are, of course, additional measures that you can take to integrate solar PV more rapidly. And once again, I wanted to highlight session 29, which deals with a duck curve in the California electricity market. And here again, we discussed several options to make the system more flexible to reduce the impact of solar PV on wholesale electricity markets in California. But now let's look at some of the measures that you can take within your conventional power generation park. Of course, these also need to become more flexible. Here again, the image of the future solar PV impact on the German electricity market in 2022, where you see these very sharp increase of solar PV when they start all operating at the same time in the morning and then end operating at the same time in the evening. So once again, you need to have power plants which are able to run these very sharp ramps. You need to reduce the must-run requirements of conventional power plants to the minimum amount possible. For instance, many old coal-fired power plants which have been constructed maybe in the 1960s, 1970s can only operate if they continue operation at a minimum of 50% of their output. If they go below this, the efficiency of the power plant really gets reduced a lot. So what they actually do is that they only reduce the power output from 100% down to 50%, but they never go down to 20 or 30%. And of course, these types of power plants, which have this must-run capacity of staying at 50% of the maximum output all the time, are not really applicable for future electricity markets with high shares of solar PV in the system. What you will also see in many markets is a reduction of the full load out of conventional power plants, while coal-fired power plants in the past might have run at a capacity factor of 80 or 90%. They might only run 40 or 50 or even less hours of the year. And this, of course, also has an impact on the economics of these power plant. If they operate in wholesale electricity markets, they might be able to earn some revenues via the rents. But if they operate under longer term power purchase agreement where the price is fixed but not the quantity is fixed, you might actually need to come to a situation where you renegotiate the offtake agreements with your conventional power plants. Here, just a quick overview of the ramp rates and startup times of different power plants. You can see, for instance, that open cycle gas turbines, state of the art, have very short startup times and can ramp up very quickly, whereas less modern hard coal-fired power plants actually can start much later. They might need a couple of hours to get started, or even half a day. And then also, in order to ramp up to 100% of their output capacity, can actually take quite a long time. So once again, you probably want to have technologies in the systems, especially when you plan new power plants, which are able to ramp up and down very quickly. And then again, you might also need to renegotiate some of the existing power purchase agreements that you have with conventional power plants. We, for instance, saw this in the California electricity market, but also in China and Japan, that a lot of these from the monopolistic times of the power sectors, you still had long-term power purchase agreements with coal-fired power plants, where you say, well, we take all of your power that you produce at a certain price. And this, of course, is undermining the flexibility of your systems, because even though your coal-fired power plant in China might be able to run more flexibly, they don't have any economic incentives for doing so. And therefore, they just keep on producing and producing and producing, even though renewable energies such as solar PV are in the system and could actually produce electricity much cheaper. And therefore, it is important to also change your power system design and go to economic dispatch. Once again, this is discussed in more detail in the next session on the merit order effect, because renewable energy, solar PV with no marginal costs come first in the merit order, and therefore they should be dispatched first, because it makes much more sense to run a solar PV plant, which is already operational anyway at zero cost, than running a coal-fired power plant where you still need to pay the whole cost for putting in the fuel, putting in the coal into the power plant in order to create an additional unit of electricity. So moving towards economic dispatch is crucial in all of the markets that are still operating in not yet fully liberalized electricity markets. A few words just on the dispatchability of renewables, especially here hydropower and biomass. What we've seen in many jurisdictions around the world, in Canada, for instance, was that the regulator put forward increased ramping requirements on hydropower. This sometimes just needed to change the actual operation of the hydropower plant. Sometimes you needed to upgrade the turbines or the other functions of the pump hydro power plant to a certain extent. That's quite straightforward. You also have the options to make biogas plants more flexible by adding storage tanks next to the biogas fire plant. Here, an image of how this can look like. So you see on the left-hand side the storage unit, on the right-hand side the biogas plant. So in the ideal case, you would then only produce biogas in hours when you have a lack of solar PV in the system, and then vice versa, also reduce your output of your biogas plants once you have access of solar PV and other renewable energy technologies which cannot be easily dispatched in the system. Looking at what you can actually do with solar PV, of course, new solar PV power plants can also be dispatched or can be ramped up and down. This is now available with remote control technology that a system operator can actually go to larger scale solar PV systems and regulate them down from, let's say, 100% of output to 60, 50, or even 40 or 20% of the output. So actually solar PV power plants via remote control become dispatchable to a certain extent, at least downward. And this is of course very important for other solar PV producers which might not have any remote controlled information technology included in the meters and in the inverters. You might also want to come up with easier and less technical ways of integrating solar PV to a certain extent. For instance, a German legislator decided, I think 2 years ago, that solar PV plants, rooftop solar PV plants in residential homes should not feed in more than 70% of the nameplate capacity into the system. Now you might say, well, what kind of regulation is this? You're actually capping 30% of the output. You don't really cap 30% of the output because these very high spikes of solar PV output only occur in very, very, very rare instances. So by reducing the maximum output of a solar PV system to 70%, you're actually just losing 2 to 3% of the solar PV output. So you're actually curtailing 2 or 3% of the solar PV, which you might criticize, but on the other hand, this really makes the integration of these systems into distribution networks much more easily. And then of course, the big question is always, are these producers compensated for curtailment that is taking place? Because curtailment is normally just taking place because you have certain limitations in the electricity grid, either bottlenecks in the transmission grid or bottlenecks in the distribution grid. So you could argue that these power producers actually have no influence on this because this is beyond what they can do. This is the job of the utility, of the grid system planners, of the grid operators. However, you see different kind of arrangements in some countries like Spain and Germany. You get 100% recompensated for any kilowatt hour that is curtailed because it's not your fault. However, in other countries, I think in France, for instance, you only get 70% compensation of your curtailed electricity units. Here, just once again, this example I already mentioned concerning Germany. So of course, in order to do this, in order to ramp solar PV systems up and down, you need to have some remote control capability via ripple control receivers. So this allows the system operator to really direct and talk to these units directly and tell them to ramp up and down in 10% steps from 100% to 90% to 80% to 70% and so on. And this has proven to be very beneficial for the system integration because you have to keep in mind that we have already integrated about 40 gigawatt of solar PV into the system, many of them rooftop systems. And it is very important to operate them flexibly and to be able to reduce their output as well in case of grid emergencies, because we only have a maximum electricity demand of about 85 gigawatts. And then you can imagine if you have already 40 gigawatts of solar PV in the systems, this creates some of the situation that we've seen in the graphs before, where solar PV and wind energy might actually exceed total electricity demand. Finally, a few words on demand response, on more flexibility on the demand side. from when looking at the industry or when looking at the different demand side flexibility options that you have in the systems, most countries start by making the electricity demand in the industrial sector more flexible, because you have to deal with a lot less actors than, for instance, in the residential sector. And you also have actors which are consuming quite a lot of electricity. Maybe your industrial sector consumes actually an overall of 30–40% of the electricity within your country. And therefore, just by tackling these 50, 60, 100 large scale consumers of electricity in your country, and by offering them demand side measures, demand side programs, you can actually already make the demand side of your overall electricity system quite a bit more flexible. So you have different type of options here. You can have load shift. That means that instead of producing, let's say, a unit of steel in my steel factory between 8 and 9 o'clock in the evening, where you already have most of the electricity demand anyway, you're actually shifting it to noon periods where you have a lot of influx of solar PV. This is incentivized by quite a lot of demand response programs around the world with certain financial incentives. Load shedding is, of course, the most expensive options, that you just say, hey, we cannot offer you more electricity, even though you want to produce an additional unit of steel in your factory. These load shedding measures can occasionally have very high prices, and you of course want to avoid it to the maximum extent possible. What is currently not yet investigated or implemented in many countries around the world are incentives for load increase. This is going to become more and more important as we see power markets move into situations where the supply of solar PV and other renewables actually exceeds the existing demand. And here the hope is that additional consumption can be incentivized quite easily, because you normally have very low electricity prices during those hours anyway, so that the additional incentives that you need for upgrading your steel units, for consuming more electricity for these purposes, might be quite inexpensive. On the other hand, you also have quite a lot of demand side response programs within the residential sector. However, you have to keep in mind that this is, of course, more complicated to a certain extent, because you're dealing with many more actors. And also some researchers argue that triggering demand side flexibility in the residential sector is much less feasible, because, well, when I'm not at home, all that is really running is my fridge and maybe my internet, and everything else is switched off anyway. So I have only very little opportunities to really change my demand curve by certain interactions. Of course, I can decide to run my washing machine during peak demand, peak supply periods. I can also maybe have other appliances in my household run when there's peak demand. And then again, some researchers argue that these shifts are actually quite negligible compared with changes that you can incentivize, for instance, in the industrial and commercial sector with much easier measures. And you also have to keep in mind, of course, that in order to trigger demand side flexibility in the residential sector, you first of all need to have a rollout of smart meters. And this of course also comes at a certain cost. And then not only the meters have to become smarter, but most of the appliances as well, which is likely going to happen in the longer term future, but maybe this is not one of the lowest hanging fruits for you in order to make your electricity demand more flexible. Finally, just a few words on storage technologies and the services that they can provide to the power system. We have an entire hour on this in session 30 of this webinar series. So this is just a quick overview. You can achieve load shifting. Of course, this is one of the primary features of storage, that you can actually shift the load or shift the electricity generation as well from 1 hour of the day to the next hour of the day. So you start filling your storage unit during hours of oversupply, and then you discharge your storage unit during hours of low supply of solar PV. But that what storage units also can do, and this is sometimes overlooked, is also to help to stabilize the electricity system. You can, for instance, support frequency response. What you can also do is reduce grid congestions by maybe having storage units located to points in your electricity systems where you frequently face grid congestions. You can also reduce, of course, the curtailment of renewable energies by, for instance, maximizing your self-consumptions within residential solar PV plus battery systems. And last but not least, for system integration, from a system integration perspective, the ramping capabilities, startup capabilities of storage units are also very high, similar to those of gas turbines, or even quicker. And of course, this is very important for stabilizing the grid and for running the very sharp ramps that you see in markets with high shares of solar PV. So here just a quick summary again of what we have discussed in the last hour. First of all, the development of solar PV triggers very important benefits to the electricity system. These are sometimes overlooked. We mentioned, for instance, the reduction of fossil fuel imports and the benefits that this has for the economy as a whole. We also mentioned reductions in emissions, not only carbon emissions, but also other toxics that come out of the stacks of coal-fired power plants, such as SO2 and NOx, which then again has very important positive effects on your public health system and reduces the costs in there quite considerably. Increasing shares of solar PV would also then again, of course, require a more flexible power systems. Here you have a variety of options of making your power system more flexible. We discussed all of them, like grid expansion and more dispatchable conventional and renewable power plants, flexibility from wind and solar PV, demand response and storage. So please take all of them into account. And even though, for instance, your fossil fuel-based industry might be very opposed to making their power plants more flexible because that might also undercut some of their revenues, you might have to be aware that this is often the cheapest options for making the system more flexible from a macroeconomic perspective. So some of the battles that you have with the conventional power sector might be inevitable to a certain extent. And as mentioned before, each and every country needs to analyze and compare these different flexibility options to come up with the best solution for their country. Here, just a quick outlook on session 28, which is the next session on the merit order effect. We mentioned this already several times during this webinar, that in the session 28, we will look at the impact that solar PV has on wholesale electricity market. And here, the impact are twofold. Well, the impact is actually only one, and that means that adding no fuel cost technologies such as solar PV to the system, adding technologies with no marginal cost to the systems actually shifts the merit order to the right, and therefore also the market clearing price gets reduced. This is very beneficial to all of the consumers of electricity because they will have to pay less for their electricity. But on the other hand, this also undermines the ability of solar PV and also all other power generation units to maybe refinance themselves via the rents that they achieve on wholesale electricity markets. So in this webinar, we're also discussing measures that policymakers can take in order to stabilize wholesale electricity market prices, even though a lot of solar PV and other renewable energies are added to the system. So as always, here again, you will have some further reading. There has been a lot of reports recently that have been published on optimal system integration of solar PV and other renewable energy technologies. So you can spend at least 2 weeks reading on these subjects. I hope you have enjoyed this. I also hope to hear you again in the next webinars on system and market integration of solar PV. Thanks again to the International Solar Alliance and the Clean Energy Solutions Center for providing this important platform. And last but not least, some quick knowledge checkpoints, some multiple choice questions for you to figure out whether you have actually understood the most essential parts of this webinar. So thanks again for listening, and talk to you very soon. Bye-bye.